Moving forward with chapter 11, we want to talk about saturation limits. So we've already visited the idea that a saturated solution has the maximum possible amount of a given solute, right? You have a limit to, just because something is soluble, you can't necessarily put an infinite amount. You can't just keep dissolving salt into water. For a given volume of solvent, you can dissolve a certain amount of your solute, right? So for 100 milliliters of water, you can get 36 grams of sodium chloride to dissolve. If you're at that limit, we call it a saturated solution. That is, you've dissolved as much solute as possible, and any more you put in will not dissolve. So that is the limit of homogeneous mixture. Any more solid you put in after that is going to stay solid, or whatever it is. It'll separate out and be a heterogeneous mixture. So unsaturated means you're below the limit. You still can dissolve more. You can also have what's called super saturated, where you have more dissolved than is possible. You have to try to accomplish this. You can't accidentally make a super saturated solution, but it is possible. And hold that thought, we'll come back to it in chapter 12, what that kind of looks like in the effects of super saturated, why and where that comes from. So this idea of saturation, we know it's the limit, and it kind of can overall affect solubility. And importantly, saturation varies with temperature. And so what that also means is that the amount of the relative solubility of a given substance also changes with temperature. We can see on this graph, what you're seeing is each line is labeled with the compound. And you can see the variation. That limit you're showing is the total maximum. That's the saturation limit. So for example, for ammonia, so for NH3 at 10 degrees Celsius, 70 grams is the maximum solubility per 100 milliliters. You'll note these values are all per some volume of water. So more water makes sense. You can dissolve more solid. You'll note that for most of the salts, so the ionic compounds, solubility increases as you increase temperature. So making it warmer means in general the saturation limit increases. It's not always true. You will note we do have an exception. Cerium-3 sulfate, right? I don't even remember the exact name of that element. Not something you've heard of. One of the things you can always kind of think of, the more obscure the elements involved in the compound are, the more likely it is a very extreme exception, right? You've probably never even heard of cerium as an element. This is very uncommon. For most salts, if you want to dissolve more of that salt in the solution, you increase the temperature, right? So you've put in all your salt and it's still not dissolving, crank up the temperature and you can get more to dissolve. It doesn't always change a ton. You will note that for sodium chloride here, the solubility is pretty flat with temperature. For potassium nitrate, it changes a ton, right? You go from 10 grams to over, you can break over 200 grams. So it is a pretty huge jump, and it really depends how much the variety is. And I will note, you'll note ammonia is a covalent compound, and it's decreasing over temperature. That's much more common for covalent compounds. When we're talking about ionic compounds, the solubility almost always increases. So we want to be able to use one of these graphs to kind of predict or figure out solubility. So determine if 80 grams of each solute will fully dissolve in 100 milliliters of water at 60 degrees Celsius. Okay, so I've got ammonium chloride, potassium nitrate, potassium chlorate, and potassium iodide. So when I'm looking at working with one of these graphs, you'll note we always have to be told the volume of water that we're dealing with. That's an important first step. This is mass per 100 milliliters. So I am told that I'm dealing with 100 milliliters of water. That's an important thing to consider, that I can only use this graph directly if I'm dealing with 100 milliliters of water. So important thing to make sure you're dealing with. When you're actually using the graph, once you check that, temperature is what we want to check. So we're at 60 degrees Celsius. So these are the conditions our solution is under. We want to be checking based off of that. When we're dealing with ammonium chloride, once we're picked 60 degrees Celsius, we just find where our line intersects 60 degrees Celsius. we can see that at that point, at that temperature for ammonium chloride, only 55 grams is soluble. Now, that's not a very precise measurement, but importantly, we're trying to determine if 80 grams is soluble, and we are certainly below that, meaning no. If you put 80 grams of ammonium chloride into 100 milliliters of water, only 55 is going to dissolve. There will be some left over, and you can predict 80 minus 55, 25 grams will be left over undissolved. You'll just have solid ammonium chloride sitting at the bottom of your beaker. If we move to potassium nitrate, we're still at 60 degrees Celsius, but now we're on a new line. We're on potassium nitrate. We can trace that over. At 60 degrees Celsius, you can dissolve 100 grams of potassium nitrate. That is greater than 80, so yes, all 80 grams of your potassium nitrate will dissolve, and you could keep going. Potassium chlorate, you can see, is down here. Kind of a weird intersection, but this potassium chlorate is what we're looking at. You can see down low, only 25 grams can dissolve, so no, not even close. Not even half. You got most of your solid would stay as a solid in the bottom of your beaker. Potassium iodide, we can see goes off the chart. We don't know what the solubility of potassium iodide is at 60 degrees Celsius for this chart, but because the chart caps out at 150, it's over 150, so yeah, we can do 80. Beyond that, we want to just not figure out can it all dissolve, but kind of think how we would make it, how we can affect changes in solubility, especially using temperature. So at 25 degrees Celsius, 60 grams of KNO3 is added to 100 milliliters of water. So first, how much remains undissolved? So I find 25 degrees Celsius, it's going to be in the middle there. If I go to KNO3, if I find that at 25, it's kind of intersecting. You see KNO3 is right here. This is our line. So it's intersecting right there. It looks like you could trace that out. About 40 grams dissolves. So 40 grams dissolves. So our question is how much is left over? How much would stay in the solid undissolved? We would do the difference. So 60 grams minus 40 grams is going to give me 20 grams left over. So that'd be 20 grams that does not dissolve, it stays solid. If you poured it all in, there's some solid potassium nitrate in the bottom of your beaker. Well, what about if I change the temperature? What happens if I go up to 70 degrees Celsius? Well, now if I go to 70 degrees Celsius, that same line has some pretty sharp changes. So it's going to go all the way up here. I can now dissolve 130 grams total can dissolve. I'm only trying to dissolve 60 though. So all 60 does dissolve. So at 70 degrees Celsius, 60 grams of potassium nitrate would give me an unsaturated solution. All of it dissolves and more can go in. I don't have to put in more, but I could. I can add more and it will dissolve. I won't get leftover solid until I hit 130 grams of potassium nitrate added in. Participation 121, question 4. Of those given on the graph, list the salts where more than 50 grams of the salt can be dissolved in 100 milliliters of water at room temperature, which is 25 degrees Celsius. This is the fourth question on participation 121, due Friday, January 21st at 11:55 p.m. over on Blackboard. Link to the assignment is right below the links to these videos. Again, of those given on the graph, this one right here, list the salts where more than 50 grams of the salt can be dissolved in 100 milliliters of water at room temperature, which is 25 degrees Celsius. It's a pretty good approximation of kind of the temperature we tend to live at and tend to set our labs to, at least on the AC. So yeah, you should give the names of those salts. Another participation question in this video. Just, yeah, we got one more video. See you there.